In each round of the game, f is different. And we call a function f from vertices to terminals. F is zero extension function, such that f of t is t for any terminal. So the zero extension problem, let's say minimum C of u and v, d of f and u and f and v. We repeat this many times. This d is a uniform metric on terminals k, and so this we call it opt, the minimum of this opt, and then the Carzanov relaxation. I mean, it's an extension of a metric to all this. Metric just restricted on terminals to all of the vertices. So that's why it is important, because you are just minimizing C of u and v, beta of u and v. Beta is a semi-metric on all of v, not just k, as it's written here. So beta is semi-metric on all of v, all of your vertices. But if you restrict it on just the terminals, you get what you have defined before. So this d is here. So if you restrict it on terminals k, you see that both of them are the same. And Rao and Talvar, I mean, using their popular article, they showed that the opt is between opt star, and so they got a factor of log k over log k approximation. I mean, their second algorithm the first was just a review of CKR, but their second algorithm, which was their own algorithm, they proved that it is much you can do with this factor. So it is a better approximation than the original CKR algorithm, because the CKR algorithm was just O log k, but they improved this to this. So it is a better algorithm. We can define the capacitated graph G of f on k that results from the function Cf of a and b is C of u and v. And so we have some kind of a graph G. Let's say this is a graph G, and G of f, when you solve your zero extension problem, and then after that you round it, and after that you contract the edges until that you just the remaining nodes are just terminals, then what you get is just this graph, which is B is f of v, A is f of u for any path from u to v. So you get this, and this is C of f. So this is the contracted graph. So you solve the zero extension problem, and then you do randomized rounding using CKR algorithm, for example, or you may use the Talvar better approximation algorithm, and then you contract the edges such that the remaining nodes are just terminals. And what you get is this. Put it in your pocket and go, because it's very simplified. So we say that g of f generated by f is a zero extension of g. So it's very beautiful because the contraction that David Karger used, now we can do it in a more systematic, more structured and mature way to represent, and we can analyze it much easier. You know, something like augmenting path, residual graphs, those things are some cool ideas for max flow, but you cannot analyze them very easily. Here we have a different scenario. Yeah, if you contract using a David Karger, you cannot analyze it unless you do what you are doing. I mean, you said that, okay, we are just focused on zero extension problem, and after solving it and using the randomized rounding of CKR algorithm, we just contract the terminal, the nodes such that the remaining nodes are just the terminals, and after that what we get is our sparsifier. So it's so systematic. And the claim is that we can claim that hk of u is less than hf of u. So this is a cut function of g of f, the simplified graph. And the proof is very simple. So we let u be a terminal, and we let f minus 1 of u to be all of a, such that f of a is u. And if you just take the union of all of these for any u in u, then by definition hf of u is h of a, and because a has intersection with k, which is u, and this implies that h of a is greater than hk of u. So this is the second result that we get, and this is the first result that we get, and this is our cut. But this cut is restricted to terminals, and from 1 and 2 we can say that hk of u is less than hf of u. For example, let's say I have an example, but it takes time to say, but it's very easy. You can handle it yourself. What I want to say is just to review the two-person games in problems in graph, I mean. So what do we mean by two-person games? First, I just review the LP primal problem. We want to minimize, so LP primal problem. You want to minimize C transpose X, and such that AX is B. This is n by n, for example, n by 1. So this becomes m by 1. And m, assume, is less than n. So x is greater than 0. I mean, x1 is greater than 0, x2 greater than 0. There are many methods to solve this linear programming. We have three famous methods. Method 1 is Simplex Method by Danzig. It looks at corners. It's like the steepest descent on corners. The second approach is Interior Point Method, of the work of people like Carmarker. So we go through the interior of feasible set instead of just going to the corners and the steepest descent on corners. We go through. And the third approach which is theoretically interesting but is not used in practice. I mean, simplex is more obvious. When you do Python, you get good solution very rapidly, although it is exponential and in ellipsoid is polynomial, but the world in actuality is different. So what you get in the ellipsoid method can be a good solution as well, but it takes in practice we prefer simplex method. So the dual problem, the dual LP, is just maximum of B transpose Y such that A transpose Y is less than C. Remember that the primal was minimum of C transpose X such that AX is equal to B and X greater than 0. So the dual of that is like this. And so if you solve one, you get the other one. And the weak duality is that B transpose Y is less than C transpose X. And you can write it as X transpose C, no problem, any feasible X and Y. So the proof is very simple because you just substitute. Instead of B, what is B? B is this, AX. So just substitute that. So X transpose, A transpose, we don't know from linear algebra. And this one is just less than C. And this one is just C transpose X. So we got what we wanted. And so the duality is that B transpose Y star, the extremist case, is X star TC. I mean, so this is of course, it is related to von Neumann minimax. Max min is min max in saddle point. It's like many examples in science. For example, max flow is in min cut, and many generalized examples that I've just explained. So everything should cross the middle. For example, in max flow min cut, you have some source, you have some sink. For example, this is a nice example. 11, 3, 5, 4, 2, 8, 19, 12. This is the capacity. 1,000. And so you might say that, okay, a good cut could be like this, a cut of 14. And you know that the maximum sink is less than 14. So you see why max flow cannot be more than the min cut. So the capacity of cut is the sum of the capacities crossing the cut. And that's the saddle point. So what is two-person game? As I said, we have two persons, X and Y. So flow player, Y1 does strategy 1. And if he plays strategy 2, it is Y2. Same thing for X player. If he plays X1, strategy X1, or he could play strategy X2. And by the way, X are cut player, and flow player. Y is flow player. So different combinations. For each of them, we have a different payoff. So this is a payoff matrix. So for example, this payoff. You can see that easily this is the optimal point, saddle point. So X is minimizing in primal, Y is maximizing in dual. So at min in primal and Y is maximizing in dual. And so you may say that, for example, this is another example, 1, 8, 2, 4, but this is not saddle point, so we use a mixed strategies and we don't go through that. We just wanted to introduce that zero-sum game. So why this is important? Because the extension quality game is essentially a zero-sum game. So I talked about extension quality game. So the extension player P1 chooses a zero extension, F. The quality player P2 chooses a cut from 2 to the K. And K is a subset of, K is terminal, subset of your vertices. So we say that P2 wins HKA units of capacity crossing the cut A and K minus A in P1's extension. So here we have two players. The extension player and let's call it F1, F2, and the quality player. Quality player plays, for example, A1, A2 is a cut player. It's like cut matching game. No, it's not like cut matching game. So so the payoff that we designed in the previous simple example, now here is just the payoff. This is the payoff. Payoff of strategy F, for example, F1, or strategy for quality player A. Then what you get is just the sum over the identity of FU and FV in delta K of A, C of U and V. So it's like the payoff is like here, for example, N of F1 and A1, N of F2 and A1, N of F1 and A2, N of F2 and A2. So P1 doesn't like to have many crossing edges. I mean, the extension player doesn't like to have many crossing edges. But P2 loves to have many crossing edges to prove to the extension player that his extension is bad, is terrible. So the expected payoff is X transpose Py for player 1 and minus X transpose Py for player 2 if they play a mixed strategy. So we don't go through that, but we just say that both players have exponentially sized strategy spaces in this game. And since this is a finite game, we can just use Neumann minimax theorem to get value of the game. Now I introduced the article of Harald Reiki and Gunnar Tolvar. I think he's in Microsoft and he's in Munich in Germany. as I remember. So their article is, of course, many other